So good day guys, welcome to this class. And in this class we are going to be talking about dielectric, right? In this class we are going to be talking about dielectrics. So what do we mean by dielectrics? That will be very important in this course. What do we mean by dielectrics? I would like to say that dielectric are insulatory materials that are placed in between the conducting plate of a capacitor. I repeat, dielectric are insulating material. We already know what insulator is, right? Materials that do not conduct electricity. So dielectrics are those material that are placed in between what? In between what? Exactly, the conducting plate of a capacitor. For quick review, we know that a capacitor is like this. Here are two plates, right? Plus and minus. And there is a dielectric here, right? The dielectric can be air, can be oil, it can be anything, at all, in as much as it does not conduct electricity. So we want to study that dielectric now. Recall that in our first chapter we talked about dielectric constant, right? And we said that dielectric constant is what? K. Now first of all, before we go into that, let us talk about the purpose of using dielectric, or the importance of using dielectric. The first importance, write this down, is that they maintain the two large, are you getting it now? Metal, they hold the position of a two large metal by its small distance. So we can have two large metals like this, not touching each other. And what is making it not to touch each other is what? Because a dielectric is separating them. So they can act as a separator between two plates. The next importance, we have talked about one. The next important is that they can serve to increase the maximum potential difference between the capacitor. Yes, the dielectric has effect on the potential difference, as we begin to derive very quickly. And the third one is that they also help to increase the capacitance of the capacitor. Now let's talk about the relationship between dielectric relationship between, right, the dielectric constant K and capacitance. Relationship between K and capacitance. The first relationship you should know is that C is equals to K C naught. You know how we derive this, right? Because we know before that C is equal to what? We know that C is equal to KEA, right, all over A. And we said that when it is air, there will be no K, right? When it is in vacuum, there will be no K. So we can say, so this C naught is the capacitance of vacuum, while this C is the capacitance at any point. So what's the difference between this and this? If you see now, everything here can be replaced with this, right? Because they are the same thing. So if I substitute, that will C will be equals to K C naught. So that's how we have that formula, the first formula here. The relationship between capacitor and capacitance is that C is equals to K C naught, where C naught is the capacitance in free space, right? Yes, C naught is capacitance in free space. Capacitance in free space. This class is going to be a very long class, right? And C is the capacitance at any point, or the normal capacitance. So we are done for this now. Also, we have talked about relationship between K and C. Let's talk about relationship between K, dielectric constant, and permittivity constant, E. The relationship is given as A, permittivity constant, is equal to dielectric constant multiplied by permittivity constant of free space. Are we there? Okay. Also, relationship between K and voltage or potential difference. The relationship here between K and potential difference is that K, are we getting it now? Is that K is equal to V naught over V, or in this case now it's now V naught is equals to KV, not like the other way around where we have naught attached to K like this, C naught attached to K. In this case now V naught is KV. Having this in mind, let's talk one more before we begin to solve the problems that are associated with this course. Now, let's talk about the relationship between charge density. I've talked about how many relationships now. I hope you are taking notes. Charge density. What's the symbol for charge density? Charge density is sigma, right? And K. Charge density is equal to charge density, are you getting it now? Is equal to, this is induced charge density, that is the voltage that is being induced at that point, is equal to the normal charge density 1 minus 1 over K, bracket close. So if we know all those things now, we can now go and be solving questions. Like I said, I'll be doing selected problems, right? Yes. So let's see how it goes. The first question here we talk about is example 6.2. Example 6. Sorry, I think example 6.2 is similar to the exercise we did before, so we'll leave that for now. Yeah, it's example 6.2. Example 6.2, if you check, is similar to exercise 5.2, and we did it in the other class. So let's go to example 6.3. Example 6.3. The first step in learning is first of all acknowledging that what you are learning is not hard. That is the first step. No matter how tough it is, you must first of all acknowledge that what you are learning is simple. A sheet of plate that is 50 cm wide. We'll talk about 50 cm wide. What are we talking about? Talking about the length, right? Or the breadth, anyone. So it's a sheet of plate that is 50 cm wide and 0.2 cm thick. Between metaphor of same weight is used to make a 4 micro ohm capacitor. If the dielectric constant of the capacity of the plastic is 2.8, what is the length of the plastic required? What is the length of the plastic required? Let's read this question again. A sheet of plastic 50 cm wide, right? That is talking about breadth, and 0.2 cm thick is used between metal foil of same width to make a 4 ohms capacitor. Like I said, I don't solve this question before teaching, so I'm just solving it directly. It's very easy. See, the thing, I have to read it twice before I get the logic. Once you understand the concept, the solution is just mathematics. When the plate is thick, right? This is thickness, right? Everything here is thickness. Is it not? This is thickness. If we have a capacitor here, no matter how wide it is this place that the metal plate will be at. It is this place. Let's say this is the plate between the conductor. Are we getting it now? Let's call this one plate 1 and plate 2. So this plate 1 and plate 2 are separated by the thickness of this plate. Are you getting it now? Yes. So that thickness, we'll take it as distance between the plates, right? So distance between the plate is same thing as the thickness. That's same thing as what? 0.2 times 10 raised to power minus 2 cm. But in this case now, they gave us in cm. So what are we going to do? We convert to meter, right? So that will be minus 4 meter. For those of you asking how is it minus 4 or how did I just get minus 4 so quickly? If you divide by 100, right? This is same thing as 0.2 times 10 raised to power minus 2 times 10 raised to power indices, standard form, right? That is plus 2. But when that plus 2 goes up, it becomes minus 2. Minus 2 minus 2 is what? Minus 4. So that's how I got that. So we can continue now, right? So they gave you the breadth here. They gave you the breadth to be 50 cm, and that is 0.5 meter. So they gave you the capacitance. They say if the constant of permittivity is 2.8, that's K, right? That's K. Sorry. If the dielectric constant, note, dielectric constant K and relative permittivity is the same thing. They are the same thing. So they're talking about dielectric constant or relative permittivity, they are talking about the same thing. So they gave you dielectric constant K or relative permittivity, anyone, to be equal to what? 2.8. So what is the question? Find the length required. This is my mind, it is easy. First, what I will do is that recall that capacitance C is equal to epsilon K epsilon naught area all over D. Is it not? The capacitance that be given to us, they say that the capacitance is 4.8 microfarads as C. The area is not given. So to calculate the area is equal to length times breadth, right? And the length is not given. The length is what we are looking for, but the breadth is 0.5. So epsilon of free space, we already know epsilon of free space, right? We know the value to be 8.85 times 10 raised to power minus 12. Then the D here is 0.2 times 10 raised to power minus 4 meter. If we are correct here, that means that we can plug in everything into this formula, right? We can plug everything into this formula here. What formula are we talking about? This formula. To have C, that is 0.4, that is 4.8 times 10 raised to power minus 6, that's for C. To be equal to K now is 2.8, right? Epsilon is 8.85, right? Times 10 raised to power minus 12 times area area here is what? Length times 0.5. How do we get that? Look at it. All over distance, that's 0.2 times 10 raised to power minus 4. So everything here is just mathematics, right? We make a subset of formula. To do that, take this one to this side. That will be multiplication, right? So 4.8 times 10 raised to power minus 6 times 0.2 times 10 raised to power minus 4. Sorry. Minus 4. We have taken this to this side now. This one is like cross multiplying. This one will go down, right? So that will be all over, everything here will go down. 2.8 times 8.85 times 10 raised to power minus 12, right? Including the 0.5 will also come down. It's like cross multiplying. Take this one here, take this one here. What we will only leave is what you are looking for, that's L. So 0.5 will go down, everything equal to L. So if we evaluate this, you will have the value of L to be equal to 6.46 meter or 6.5 meter. That's the answer. Example 6.4, I will treat it specially. It's under transient. I will treat it specially on a separate video. So in this question, example 6.5, that's in page 60 in this edition. I don't know. So a parallel plate air capacitor is charged to a potential difference of 250 volts, right? And then connected in parallel with another capacitor of equal dimension with ebonite as dielectric. The potential difference of the combination is to be 50 volts. Calculate the dielectric constant of ebonite. So in this question now, it's just everything I said, everything here is just like what we solved in the previous exercise, but let me explain. This capacitor now, let's say this capacitor C is receiving voltage, right? 250 volts. Now this voltage, this capacitor now is now powering another capacitor from the voltage received from here. So it's like power is entering this capacitor and this capacitor is discharging to another capacitor. So what do we do now? First, we'll look for the charge that is entering the first capacitor. Listen very carefully. It's like this, the charge that is entering the first capacitor. Remember that Q is equal to CV, right? From C is equal to Q over V, you know now, right? So the charge that is entering this capacitor here, that charge now will supply the parallel connection, of C1 and C2. The first charge entering this capacitor is CV, C1, V1. Now this capacitor is now connected in parallel with another capacitor, right? So that parallel connection is being sponsored by this charge here. So we can rewrite to say that C1V is equals to C1V1. Are we getting it now? Plus C2V1. Now the problem is which one is V and which one is V1. You can call it V1, V2, but so far you know what we are talking about. What voltage will be here? This voltage here will be the supply voltage, right? Like the voltage that is entering the first capacitor. But which voltage is here? The voltage that will be here is the voltage that the second capacitor is releasing, is the voltage that the first capacitor is now releasing to the second capacitor, right? So let this V1 be, let this V be equals to 250 and our V1 be equal to 50, right? So what's C1? We already know that C1 is not given here, or they told us that the capacitor is A, so we can write it as K, right? E naught area all over D multiplied by V to be equal to K E naught, it will still be the same thing, right? C1 A all over D V1 plus, now if you read the question, it says of equal dimension. What do we mean by dimension? Area, distance, dimension. So it means that this C2 will also have the same area A, the same distance D. Now what will be different here is the constant of permittivity, K E naught. But note, since this C1 here, they said C1 is air capacitor, right? Air capacitor. So since C1 is air capacitor, what will happen to K here? K will be equal to what? 1. So in this case now, K is 1. So I can clean off K. Since 1 multiplied by 8 will also give me 1. So I can clean off K and just leave it like this. Here also I can also clean off K, right? But this one I cannot clean it because it said that find the dielectric constant of ebonite. So this is not air, this is ebonite. So K will not be 1. So we'll leave it like this. So all we just do is simplification. So let's simplify. This will be E naught A over D multiplied by V. But please note that we have V1. This place is also V1. So V1. Right? So let's factor out what is common is epsilon A over D. Epsilon A over D. So we'll bring it out. Epsilon A over D bracket V1 plus K V1. So if they cancel out here, what should you have? Right? So you will have V equals to V1 plus KV1. So also here, you can factor out to say V is equals to V1 plus, V1, are you getting it now? If you factor out, here will be 1 plus K, right? So if that is true, we will now have V is equals to V1 1 plus K. So we now substitute. We said that V is 250, right? And V1 is 50. 1 plus K. So if you divide through, that means that 1 plus K is equals to 250 over 50, which is same thing as 5. So that means that K is equals to 5 minus 1. That's 4. It's easy, right? Very easy. So after this, we're now going to the exercises. Let's go to the next question now. This is example 6.6. 3 capacitors, each of 100 picofarad. So it means that 3 capacitors have 100 picofarad, right? Are charged to 300 volts in series. I'll get it now. A. Determine the potential difference at the end of the plate. B. Determine the charge on each capacitor, and E. Determine the energy. This is very easy. It says 3 capacitors of what? 3 capacitors of what? 3 capacitors of 100 picofarad. So that means C1 is equal to 100 picofarad, which is the same thing as C2, also equal to C3, are connected in series, right? Now note, in series connection, the potential difference is not the same, but the charge is the same. We know this before, right? Yes, in series, if you don't know it, you can note it down. In series, the potential difference varies with different capacitors. So that means that to get the total potential difference, you have to sum the potential difference on each capacitors together. So they say that are charged to 300 volts each. So it means that C1 has 300 volts, right? C2 has 300 volts, and C3 has 300 volts. So they say determine the potential difference between the plates. That means that determine the overall potential difference. That's what they are trying to say. So the overall potential difference now, this C1 doesn't mean capacitors 1. No, it means, okay, don't worry, let me clean it so that it won't look confusing here. When I mean C1, I mean, okay, let's just call it V1, V2, V3. So the total voltage here will now be equals to V1 plus V2 plus V3. That's equals to 300 plus 300 plus 300, right? That's 900 volts. Question 2 here says that what is the charge on each plate? Very easy. Recall, right? On each, we are not saying the total charge, on each. So each plate has a normal voltage of 300 volts, right? Yes, this is our V. What of our C? Our C is 100 picofarad. Pico means 10 raised to the power 12 F. So to get our charge, remember that C is equals to Q over V. If you make use of it of formula, Q will now be CV, right? So that will be equal to 100 times 10 raised to the power minus 12 times 300. So if you multiply this will give you the sum of 3, right, times 10 raised to the power minus 9, or 30 nanocoulomb. It's as easy as that. So the next question I want to solve here now is B. It says find the energy stored in the system. If we are talking about the system now, it's talking about the total, right? Total system. So the V we are going to use here is 900. But assuming they say find the energy stored in each plate, that means you are using 300 because each plate carries 300. Okay. Now remember the energy stored in the capacitor. Energy stored in the capacitor, E, is equals to what? It's given by the formula 1 all over 2 CV squared. Now to get our C is the equivalent capacitance, right? To get this now, we have to use capacitance in series. And the formula for capacitance in series is what? 1 over C is equals to 1 over C1 plus 1 over C2 blah 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 1 over Cn. Right? So here 1 over C, 1 over, what's our C1? Our C1 is 100 picofarads, right? PF plus 1 over 100 PF plus 1 over 100 PF. So everything depends on your mathematics techniques. Me now, what I will do, since everything are the same, it will only work for when they are the same. If they are not the same, you just use your normal SCM method. Or why not just press the calculator? Why not just press the calculator? Are we playing? Okay, let me just write. So here will be 1 plus 1 plus 1. So that's 1 over C is equals to 3 over 100. And if I invert it, that means that C will be what? 100 over 3. That will give me 33.3 picofarad. And pico means 10 raised to power what? Minus 12. Is it not? Farad. So I've gotten my C, I've gotten my V. So all I just need to do is to input it here to have 1 over 2 times 3.3 10 raised to power minus 12 times 900 square. And if you do this carefully in your calculator, you will have a value, right, as 135, approximately 135 times 10 raised to power minus 5 joules. So thank you very much for watching this. In the next class, we are going to be going deep into solving the examples, the exercises that are related to this chapter. God bless you.